In this concept video, we're going to be discussing what a vector is. So a vector has both direction and magnitude. What does that mean? Well, the direction is important for a vector, the orientation, and also the magnitude, which corresponds to the length of the vector when we graph them. However, magnitude could be a few different things. So magnitude could mean distance. It could mean force, maybe even velocity or acceleration. And there's probably a number of other things that magnitude could stand for. What do they look like? We're going to make up just a couple points here, and then we're going to graph this vector on the coordinate plane. So I'm just going to pick A being 2, 4. So I'll go right to up 4. That'll be point A. And that's also going to be my initial point, or where the vector begins. Then I'm just going to pick another point B just arbitrarily, and I'm going to make it 5, 9. And that point, point B, is going to be the terminal point, or where the vector ends. And that actually is important for this. You want to know where to begin and then where to end. If we graph B, we've got 5, 9. So I think that's going to be all the way up there. When we draw our vector, the vector is going to look like a ray. But there's a big difference between a ray geometrically and a vector. And that is this. A ray would continue on forever in one direction, and a vector ends. So this vector begins right here at A, and then it ends where the arrowhead is right here at B. We can represent vector AB in component form as well. So to do that, we're going to write AB. We're going to write a line with like half of an arrow barb at the very top. And in vector component form, we're just going to write the X and the Y parts of the vector. To do that, we're going to look at vector AB, and we're going to break this down into the X part, which is this piece right here. So that's 3 units. And then the Y part, which is 1, 2, 3, 4, 5 units. Direction does matter for a vector. So we're going to move from A to B. So that would be right by 3 and up by 5. So we're going to indicate that by right 3 as being a positive 3, and then up 5 being a positive 5. So there's your vector component form, or a vector ordered pair. There's other ways of representing a vector. So let's say that we wanted to represent vector R, and we'll do this in a different color here for you. So let's say we wanted to represent vector R in component form as being from, in component form as being -2, 4. And we're also going to represent vector R in standard position. So in standard position, the initial point is right here at the origin, and then the terminal point is going to be somewhere else. And that component form is going to let us know where the vector ends. So we're going to go left 2 and then up 4. It's really similar to just plotting an ordered pair, but it's a little different when you write those sideways V's, or they're not really less than or greater than signs, but it's what they kind of look like. That's not an ordered pair right here. So for vector R, that's a vector ordered pair, which is -2, 4. And in standard position, we would write it like that. And we could put a little R here with a little line and a barb, just half of a barb there on the top to indicate vector R. So you can define a vector with the initial and terminal point, or you can actually name the vector itself. In that case, that's vector R. We're going to move on now to finding magnitude, which corresponds to the length of that vector. So I'm going to clue you in right here to vector AB. So vector AB over here, if we wanted to find the magnitude of vector AB, let's write that down here. We're going to do that with, they look like absolute value bars, but when we write the vector notation inside, it means magnitude or length. And so what we're going to do here is we're just going to use the Pythagorean theorem. So this one would be the square root of 3 squared, that's the x component, plus 5 squared. So that'll be the square root of 9 plus 25. And when you square any one of these numbers, whether they're negative or positive, you're going to get 2 positive numbers here. And that's going to be the square root of 34. If you wanted to know how to do this using the initial and terminal point, then the structure of this is the same as the distance formula. So you would take the terminal x minus the initial x, that gives you the difference between them, square it, so that would be 3 in this case. We could look at that and say, hey, here's 5 and here's 2, so 5 minus 2 is your 3. And then we have to add the difference between the terminal points y minus the initial points y, and then you can take the square root of that. So that's your formula, and to actually do this with our vector AB, that would of course be the square root of 34. So let's talk a little bit about distance and displacement. So in terms of distance, the total distance is going to be equal to the total traveled. You could even think about this as ground covered. And this is, if you think about a car, this would be equivalent to the odometer, which tracks how many miles you've driven. And the direction there would not make a difference, right? You could go to school and back, and the total distance, let's say one way would be 5, and then back to your house would be 5. So the total distance there is going to be 10. So you'd want to add those together. It's the total traveled or the total ground covered. So let's talk about displacement now. So displacement can be understood a few different ways. You could say it's how far out of place from the initial position, how far out of place the particular item is. You could say change in position. So in our little scenario there with going to school and back, let's say it's 5 miles each way, your total distance would be 10, but in terms of where you began, which is your house, your displacement would be 0 because you returned to where you started. So your displacement in that case would be 0. And another way we're going to understand this sometimes is it's called net distance in some cases. Let's talk about 3 more vocabulary words. So we're going to talk about 2 vectors being equal. So 2 vectors are going to be equal if they have the exact same direction and same, let's see here, I should probably underline that. We'll try to do that for you. And there we go. And same direction and magnitude. Okay, what about 2 vectors that are exactly opposite of each other? So the direction is 180 degrees from each other, but the magnitude has to be the same. So in this case, you can imagine like a tug of war where the rope is not moving anywhere. And imagine that. So you had two teams that were pulling with an equal force. The rope wouldn't go anywhere, and their direction is exactly 180 degrees from each other. One group would be pulling one way, and the other group would be pulling exactly 100 degrees in the other. And the magnitude would be the same for that rope not to move. Let's talk about when 2 vectors are parallel now. And so this is where the direction is the same or exactly opposite. And then in this case, the magnitude does not matter. So magnitude can be different.